This is the final part of this course, and in this final part I combine some random topics from different areas of this algorithm theory just to give you some perspective of what's going on. And today we'll discuss number theory algorithms. Computational number theory is a large area of algorithm theory, and I'm not a great specialist in this area, so I'll just give you some introduction. If you really want to learn what's going on in computational number theory, you actually need some big course about this, but today will be just a short introduction. Okay. Let's start with simple algorithms. Let's start with finding greatest common divisor of two integers. So, say GCD of A and B. So, greatest common divisors of two integers is just what, as the name suggests, is the greatest number which divides both A and B. So, for example, well, let's have some numbers. Let's say GCD of something like 20 and 64. It will be something like 4, right? So 4 is the biggest number which divides both 20 and 64. So how to find the greatest common divisor? This is a simple algorithm. It was invented actually a few centuries ago. It's Euclidean algorithm. Euclidean algorithm uses a very simple idea. Let's look at numbers A and B. If both these numbers are divisible by some number d, then number A, so if A is divisible by d and B is divisible by d, then A minus B is also divisible by the same number d. So what we'll do, we will get from pair AB to a pair, let's say A and A minus B. No, why is it true? Why is it true? No, because again, if we have some divisor, so A is divisible by D and B is divisible by D, then A minus B is also divisible by a number D. Yeah? So each common divisor of A and B is also a common divisor of A and A minus B. From the other end, if we have some number D and both A and A minus B are divisible by this number D, then number B is also divisible by number D, because B is just equals this minus this. Yeah. So B equals to A minus B. So if we have some common divisor here, we have the same common divisor here. What we basically say that the set of common divisors of these two numbers and these two numbers is the same. So the greatest common divisor is also the same. That's the whole idea. How to apply this idea? So if you just apply this idea like this, you will say so. Okay, let's try to apply this idea to these two numbers. So we start from two numbers, let's say 20 and 64, and then just apply this formula over and over again. So we take the larger number and subtract this small number. So we get from here to pair 44, 20, then to pair 40 and 24, 24, 20, and then to pair 20 and 4, and then subtracted here, that's 16, 4, 8, 4, 4, 4, and finally 0, 4. So, and then we get a situation like this. When one of the numbers is 0, then obviously the common divisor is the other number. So the greatest common divisor of 0 and 4 is obviously 4. So that's how we find common divisor. If you do it like that, unfortunately it will be too slow. Because let's say you have some big number here. You have like number, I don't know, 1000 here and 1 here. So if you will just apply this formula over and over again, then each time you will decrease this number by 1. So the number of steps will be the same as this number. It's just too slow. So we will improve it a little bit. we will make these steps until this number is less than this number. So if a is greater than b, then we can subtract b from a as many times as it needed, so this number is less than a. Less than a, right? So instead of making a minus b, we will have the remainder of the division by b. Yeah, like this. Yes, you can do the same. So it's symmetrical formula, yeah. So you can subtract b from a or a from b. It's the, yeah, by the same reasoning. So a and b I could symmetrical, yeah. Why is it true? Again, because what is the remainder of a divided by b? Remainder divided by b is just a minus a divided by b rounded down multiplied by b. Yeah, that's just definition of the remainder. Yeah, so we divide a by b, get the integer part of this fraction, and then multiply by b, and then subtract this many copies of b. And just by the same reasoning, if we have common divisor here, we have the same common divisor here. So the final algorithm looks like this. Okay, let me just write the usual implementation. So we will set the following algorithm. We'll say GCD A and B. We will look at the number b. If number b is 0, then the greatest common divisor is a. If not, then we'll divide a by b, get the remainder, and call recursively. Let's return. Let's say return GCD of b and yeah. So here I just swapped them because I want the first operand to be greater than the second operand. Okay? So I want to maintain property that a is always greater or equal than b. Yeah. So when here when I call it recursively, I say b is greater or equal than a remainder of a divided by b. Yeah. Because the remainder is always, yes, the remainder is always between 0 and b minus 1, right? That's all. That's the full algorithm. A very simple Euclidean algorithm. That's all. And the first time we'll confirm. Yes, the first time when you call the function, you want a to be greater than b. If not, then actually the first iteration will not satisfy this invariant, right? So if you call this function and a is less than b, then what will happen? You will go here and say b and a modulo b. A modulo b, if b is greater than a, will be just a. So if a, it's a. So if here a is less than b, then here we will say b and a. So a modulo b will be just a. So even if you call this function and a is less than b, then in the first iteration, you will go here and call the same function with swapped arguments. Yeah? So it's very simple code. It works perfectly, actually. One of the simplest algorithms in this theorem. Again, let's do it again. So let's say something like 64 and 20. So we will say b, and also we have 20, and 64 modulo 20 is 4, right? Then they take 4 and 20 modulo 30 is a 0, and further have 0. Just in 2 steps we find the greatest common divisor. Okay. Now let's calculate time complexity of this algorithm. How many recursion steps can we make until we have one of the numbers equal to 0? It turns out we can make at most logarithm steps in this recursion. Why it is so? Because each time we move into this recursion, we decrease number A at least twice. Let's see. So I claim that here A modulo B is less or equal to A over 2. Why is it true? Why is it true? No, let's see. Let's make two cases. So if B is less than A over 2, that's how it will. Then A modulo B is less than B, so it is less than A over 2, right? So if number B is less than half of A, then this modulo will be less than half of A. So we will decrease number of A at least twice. If it is greater than A over 2, then A modulo B is at least A minus B. Actually equals A minus B. And it is still less than A over 2. Again, why is it true? Because you have some. So again, the remainder of this division is just A minus some copies of B. How many copies of B can we fit into one number A? At least, at most one, because B is greater than half of A. So we'll put exactly one copy of B inside A, right? So so again, A modulo B is A minus A over B multiplied by B, and this equals to 1, because B is greater than half of A. Yeah? Okay. What does it mean? It means that each time when we call this recursion function, we decrease one of the numbers at least twice. We can decrease number twice at most log n times. So the time complexity of this algorithm is, let's say, log n, where n is something like A and B less than n. We can say log A plus B, something like that. Now, let's stop here. I would say that this algorithm has polynomial time complexity. What does mean polynomial time complexity in this number theory? In number theory, complexity is measured, usually how do you measure complexity? You measure complexity compared to the size of your input. Yeah? Size of the input, if you have only numbers, the size of the number is basically number of digits in this number. Yeah? So we measure complexity from the number of digits in the number, and number of digits in the number is basically logarithm of this number. Yeah? So we measure complexity not from n, but from log n. So if we want our time complexity to be polynomial, we want it to be polynomial of the logarithm of n, not of n. Yeah? So this is a polynomial algorithm which calculates the greatest common divisor of the numbers. Actually, when you use this number theory, and it's mostly used in something like cryptography and something like that. Yeah. So in cryptography algorithms, they use very large numbers. They use like, I don't know, 500 bits numbers. Yeah. So this logarithm is actually not small. So it's like length of number can be up to 1,000. Let's see. So it's not we usually see in this. So usually in the algorithm we see like n is the size of the graph, or n is the number of elements in data structure. Yeah. So here number n is actually very large. So the logarithm of this number is actually big, but still this is the polynomial algorithm of the size of this number. Good. Yeah, actually, when you think about these algorithms, you need to consider not only the time complexity, but also the time complexity of these operations. Arithmetic operations, if you have big numbers, can be made in constant time. Yeah. So even if you want to calculate the sum of two numbers, and numbers are really huge, then you need to calculate these numbers bit by bit. So the time complexity of simple operations like sum of two numbers will be not constant. It will be log n. Yeah. So actually time complexity of this algorithm is log n multiplied by time complexity of this modular function. Modular function has also some polynomial time complexity. Good question. What actually time complexity? We will not talk about this that much. But you can calculate the remainder of division of two big numbers in polynomial time. Basically the same like you do it in school. Yeah. So you can just calculate bit by bit in like n square time, something like that. So in log n square time. Okay. Cool. Now let's have some problem. That's actually not the best. Usually, it's not the best algorithm to calculate greatest common divisor. So in practice, it is another good algorithm. Let's talk about another good algorithm. So usually there's a better way to calculate greatest common divisor. Okay, what is the we pointed this algorithm. This is the calculation of this remainder. This remainder is actually needs some work to do. Yeah. So if you have two big numbers to calculate remainder, is like a long process. What you can do? You can instead make another algorithm, which doesn't use this modular function. It works like this. So let's see what is GCD of A and B. Let's see. So if one of these numbers is even and another one is odd, so for example, let's say this A is even, let's say just even, and B is odd, then the greatest common divisor of these two numbers will not contain any 2's, right? So 2 is not a divisor of A and B. It is not divisor of B. So the greatest divisor of A and B will be the same as GCD of A over 2 and B. So 2 is not divisor of B, so we can divide A by 2, and the result will be still the same, right? What next? If both numbers are even, if A and B are even, then 2 is common divisor of A and B. We can get these two out of brackets and say that the greatest common divisor of A and B is 2 multiplied by GCD of A over 2 and B over 2. So we just know that 2 is a divisor, so we get 2 out of this function and calculate the greatest common divisor of these two things. And finally, if both integers are odd, then we can subtract. Let's subtract A from B. When we subtract A from B, or B from A, doesn't matter, the result will be odd. Yeah. So again, so GCD will be equal to GCD of A minus B and B. This thing is even, this thing is odd. Yeah. So again, 2 is not common divisor of these two things. So we can divide this thing by 2 and get the same result. That's all. So again, we have 3 cases. No, actually 4 cases. Here we have the same case and the same case. Yeah? And for each of these cases, we have one of these formulas. In each of these formulas, we divide something by 2. Yeah? So the number of steps in this recursion will still be log n. But what's the difference? Here we calculate we divide long integers, but we divide it only by 2. Here we divide integer by b, we divide one long number by another long number. Here we divide long number by some short number by 2. And divide number by 2 is much easier than divide one long number by another long number. Actually, if you have bit numbers, you can just shift the number one bit to the right, and it will be the result of division by 2. So here the number of steps again is log n, but instead of calculating this remainder, we calculate the result of division by 2, and it is much easier than calculate the remainder. Yeah. So this algorithm uses log square time, I think. So you can divide. So you can divide linear time. So, and here you need to calculate the difference. You can subtract one logarithm in the linear time. So so you can make all these operations in log n time, and the number of steps will be log n. So it will be like log square, right? Whew. Okay. Next interesting thing. So Euclidean algorithm is not only used to calculate greatest common divisor. It has multiple interesting purposes. For example, what you can do using Euclidean algorithm. You can solve diophantine equations. What is diophantine equation? Diophantine equation is a very simple thing. Let's have equation of this form. Let's have equation ax plus by equals c. So we have some integer coefficients a, b, and c, and we need to find integer values x and y. So this equals to c. Yes, an important thing that we can solve it. We should solve it in integers. Yeah. So if you can use real numbers here, it's basically too obvious. Yeah. So we want to find integers x and y, so that this sum equals to c. How to solve diophantine equations using Euclidean algorithm? Well, first let's see. If we know the greatest common divisor of, if D is GCD of A and B, then what can we say about this number C? What do you think? So D is greatest common divisor of A and B. Yeah. So if A is divisible by D and B is divisible by D, then C also must be divisible by D. Yeah. Because this part is divisible by D, this part is divisible by D, so C must be divisible by D. So if C is not divisible by D, obviously we have no solution. Now, I claim that if C is divisible by D, there is always a solution. Why is it so? Because let's solve the following equation. Let's solve this equation instead. I claim this solution always, this equation always have a solution. And if this equation has a solution, then this equation also has a solution. Well, again, because C equals to something like C prime by D. Yeah. So if we solve this equation, we will then multiply x and y by this C prime and get solution of this equation. And I claim this solution is this equation always has a solution. How to find this solution? This not only has a solution, we can find this solution in polynomial time. What's wrong? Yes, okay, what's the problem? So 2x plus 3y equals to 5. So this is A, this is B. So greatest common divisor of 2 and 3 is 1. Yeah? So D equals to 1. 5 is divisible by 1. Yeah, so this solution has this equation has a solution. So there's no problem here. So C shouldn't be divisible by A or B. It should be divisible by the greatest common divisor. If you have something like that, let's say plus 4y equals to 7, then there's always no solution, because this part is even, this part is even, so the result must be even. So it can be equal to 7. Yeah? Good. Okay. So, how to find the solution? We will find the solution using the same algorithm as here. What we'll do? We will run the same algorithm, but we will return not only the value of greatest common divisor, but also the linear combination of A and B, which give you the same combination. So let's run this algorithm. Let's actually write it. Let's write it here again. So I want to calculate the greatest common divisor of a and b, and this function will return three values. Okay? It will return d and also x and y, such that xa plus let's make it like here, ax plus by equals to d. So my function will return three values. It will return the greatest common divisor of a and b, and also the linear combination of a and b, which gives you number d. Again, let's just rewrite this thing. So if b equals to 0, yep, then the greatest common divisor is a. We need to find linear combination of a and b, which gives us a. It's pretty simple. What linear combination give you a? Well, for example, 1 and 0. Cool administration. So we can return a, 1 and 0. Nice. Again, greatest common divisor is a, and combination of 1 multiplied by a plus 0 multiplied by b equals to a. So it gives you a linear combination which is equal to the greatest common divisor. Now, else. Now it's interesting. Let's run this thing and get the result for this b and a modulo b. Let's say, okay, let's say d, x, and y equals to GCD of b and a modulo b. Now, we know the greatest common divisor. It's here. And we need to find linear combination for a and b. We already know linear combination for b and a modulo b. How to find the linear combination for a and b? Let's see. So what happens here? What happens here? We have x multiplied by b equals, wait, no, equals, plus y multiplied by a modulo b equals to b. Again, what is a modulo b? A modulo b is just a minus a over b multiplied by b equals to d. Well, let's look at this equation. So let's remove the brackets. So we have xb plus ya minus this. So let's combine it. Let's combine it like this. So we have x minus a over b by b plus ya equals to d. So now we have linear combination for b and a. So we have linear, so this number is integer and this number is integer. So we have linear combination which gives us d from this given a and b. So we'll return d and linear combination of y and this thing, x minus a over b. You missed y. Where? Yeah, something wrong. Yeah, I see something wrong. Okay. xb plus y minus this equal d. I missed this one. Oh, my bad, my bad. Okay, let's fix this. Let's fix this. Yes, minus 1. Right. Yeah, that was better. It looks suspicious actually. But so y and x minus y a over b. Yeah. That was better. Cool. So this was like extended version of this Euclidean algorithm. It calculates not only the greatest common divisor, but also linear combination of A and B, which is equal to this greatest common divisor. Actually, if you have some diophantine equation, there are many solutions. So this is just one of the solutions. There are many other solutions of this equation. It happens because here we take this 0. Yeah, but here we actually can take any number here. Yeah. Instead of 0, we can take any number here. And this will give us not one solution of the diophantine equation, but just the set of possible solutions of the diophantine equation. Okay. That's all. That's how we solve diophantine equations. So again, you have equation. You check that this number C is divisible by greatest common divisor. If not, then there is no solution. If it is divisible, then you solve this solution, this equation instead. Solve this equation, then multiply x and y by this number C prime and get solution for this equation. And there are multiple solutions. You can find all of them actually. You know, there is some series of solutions, just the periodic substructure of this. Okay, that's all. That's all. Cool. Okay, let's go. Let's go next. The next interesting thing is called the Chinese remainder theorem. It's called the theorem, but we'll use it as algorithm actually. Oh, sorry. Hello. Да. Ага. Все, да? Хорошо, все. See? Sorry. So, Chinese remainder theorem. Very simple theorem. Let's take two coprime numbers. So let's take numbers n and m. And they're coprime. Coprime means just they have no common divisor other than 1. So GCD of n and m equals to 1. Now, let's take any number a from 0 to nm minus 1. And then calculate the remainder of calculate number n, modulo n, and modulo m. So let's have two integers. Have a1 will be a modulo n, and a2 is a modulo n. Now, there are nm possible numbers a and nm possible pairs of a1 and a2. And the theorem is that there is a unique So there's a unique way to go from a to pair of a1 and a2. So there's a bijection between these two sets. Yeah. Now let's see. So it's easy to get from A to this pair. Yeah. So each number is how to say? So from number A, it's easy to get this pair A to A1 and 2. The harder part is to get from this pair a number A back. Yeah. So this side is simple. So this side is a little bit more complicated. Some problem discussion? No, we'll not do it. It's just simple theoretical lecture. We'll not discuss any problems. We can do it in some streams, maybe later, not today. Now, yeah. So how to find number A if we know pairs of number A1 and A2? Again, let's have some example. Let's have some example here. For example, so let's say n equals to, I don't know, 2 and m equals to 3. So we have all possible a's, 1, 0, 2, 3, 4, 5. A1 will be 0, 1, 0, 1, 0, 1, and A2 will be 0, 1, 2, 0, 1, 2. So you may see that for any, all these pairs are different. So if you take any pair of these integers, it corresponds to some unique number A here. So the question will be how to find this number A if we know numbers A1 and A2. How to do it? Let's write the equations. So what is A1? A1 is A modulo n. What is A modulo n? Is A minus something multiplied by n. What is A2? A2 is A modulo m, so it's A minus something multiplied by m. Now, from both of these equations, let's get the number A. So here A equals A1 plus xn. Here A equals to A2 plus yn. Now let's combine these two equations. Here we have A, here we have A. So combine them and we'll see A1 plus xn equals to A2 plus ym. Right? Now let's just put this to the left, this to the right. So it will be some xn minus ym equals to A2 minus A1. Yeah? And what do we have? We have a diophantine equation. Yeah? So again, in this equation, we know number n, we know this difference. So we can solve the diophantine equation. It will be solvable because n and m are coprime. Yeah. So greatest common divisor is 1. So any diophantine equation is solvable. We will solve this diophantine equation, find numbers x and y, and then knowing these numbers x and y, we can find number A here. That's all. So again, the algorithm works like this. You want to solve this system of equations. How you do it? You combine them like this, solve the diophantine equation, find numbers x and y, and then find number A from this. Quite easy, actually. Yeah. That's all. That's all. What happens if numbers are not coprime? So what if I remove this restriction? So what if I allow numbers n and m be not coprime? Can you see what's going on? Yeah. If numbers are not coprime, then some of the equations will be not solvable. Yeah, because this difference may not be divisible by the greatest common divisor of a and b, or of n and m. Yeah? So this equation will only be solvable if this difference is divisible by the greatest common divisor of n and m. No. Yes, and solution will be not unique. Yeah, this also. Well, for example, again, let's do it. Let's do it. If we have 2 and 4, stop here. So we have 3, 4, 5, 6, 7, 1, 0, 1, 0, 1, 1, 3, 0, 1, 2, 3. Yeah. Yeah, so we have multiple numbers which give the same pair of remainders. For example, here we have 1 and 1, and here we have 1 and 1. Yeah. Actually, what you can do is to calculate, if you take a not from nm minus 1, but to lowest common multiplier of these two numbers, it will work. So for any number from 0 to the lowest to minimal common multiplier of the numbers, it will work. Okay. Nice. So what's next? What's next? What's next? What's next? What's next? What's next? Yeah. Let's move to some prime numbers. Yeah. Oh no, not yet, not yet. Let's talk about something. Let's talk about modular arithmetics. So, sometimes you want to you want to make arithmetic operations not for all possible integer numbers, but for some small set of integer numbers. So we want to make all operations just by some modular. Yeah? So how modular arithmetics work? So imagine you have only numbers from 0 to n minus 1. So we have only numbers from 0 to n minus 1. Yeah. I will not use terms like rings, fields, groups, stuff like that. I will just try to avoid all the math terms in this lecture. Let's see how it goes. Yep. Well, I just think it's an interesting thing to study. Again, this is just an introduction lecture to number theory. It's not like a course about number theory. Okay, now, what if you have only numbers from 0 to n minus 1, and you want to make arithmetic operations only inside this small set of integers? I will not talk about finite fields. Okay, let's just stop here. Okay. Now, what you can do? You can do, for example, if you can sum numbers. Yeah. So instead of having sum, normal sum of integers, you will calculate the sum modulo n. Yeah. Now, if you calculate sum modulo m, it will get the sum to be in the same small set of integers. So if you calculate sum of two numbers, the usual sum of integers may be out of this set of small integers. But if you calculate it modulo n, it will still be inside set from 0 to n minus 1. That's a cool thing. Now, if you use this sum operation, it will maintain all the common properties of plus operation. For example, you say that it is associative. Plus c equals to a plus b plus c. Yeah. So associativity of sum is still here. It's commutative. So a plus b is still b plus a, and so on. So all the common properties of the plus operation are still here, even if you take modular operation after each sum. You can subtract numbers. Yeah. So what if you subtract number? Again, modulo n. And again, you have all the common properties of subtractions. For example, if you take a minus a, let's say a plus b minus b will still equal to a, yeah? And so on. So all the common properties of these arithmetic operations will still be here, even if you take modulo after each operation. Now, you can multiply numbers again. You can take modulo after multiplication. And you will have distributivity, for example. Yeah, so for example, a plus b multiplied by c will still be equal to ac plus bc. Yeah. So this modular arithmetics keeps all the same properties as for usual operations, like for usual number, but it will keep all the numbers in this small set of integers. Okay. I didn't use term group or field or ring here. Okay, that's cool. Now, can you divide or not? How to divide in this set of integers? So I want to calculate something like a over b. Yeah. Is it possible to divide integers or not? No, let's see. Sometimes it's possible, sometimes it's not. Let's instead calculate 1 over b. Let's say b, well, let's call it b power minus 1. Yeah. How to calculate b power minus 1? Again, just by definition, b in power minus 1 is the number such that if we multiply b by this b in power minus 1, we'll get 1. Let's try to find number b in inverse, such as if we multiply it by b, we will get 1, modulo n. We can take all calculations modulo n. What does it mean? If it equals to 1 modulo n, it means that if we have b multiplied by b minus 1, we will have 1 plus something multiplied by n for some integer x. What do we have here? We have a diophantine equation, right? Like before, we know this b minus 1 min minus xn equal to 1. This is again a diophantine equation. So we know number b, we know number n, we know number 1, and we need to solve this diophantine equation. When is it solvable? Can you see it? So when can we solve this diophantine equation? Okay, this is an easy question. Yeah. Then greatest common divisor is 1. Greatest common divisor of what? Greatest common divisor of b and n. So this equation is solvable only if b is coprime with n. So what does it mean? It means we can divide numbers if the number is coprime with the modular. Yeah? So we have modulo n. If number b is coprime with n, then we can divide by number b. And we can actually do it in polynomial time. Again, we can do it in polynomial time just by solving this diophantine equation using Euclidean algorithm we just discussed before. Yeah. So you use the Euclidean algorithm to find this b power minus 1, and then you calculate that's this b inverse, and then you can divide by the number b. Nice. For example, if n is prime, yeah. For example, if n is prime, then you can divide by any number except 0. Yeah. So if n is prime, then all integers from 1 to n minus 1 are coprime with n, just because it's prime. Yeah. So if n is prime, you can divide by any number except 0. That's one of the cool things about division in these fields. Okay. Nice. Yes. If n is prime, we can calculate the inverse in the integer easier. We will do it. We will do it in a few minutes. Now let's talk about prime numbers. What about prime numbers? So you have a prime number p. Let's see how to check if it is prime. Actually, quite common problem is to find a good prime number. So for many for many cryptography algorithms, sometimes you just need to pick some big random prime number. And usually how you do it is just to pick random numbers and check if this numbers if the number is prime. That's a common way to find the prime number. So how to check if the number is prime or not? Again, easy algorithm is just to check all the divisors with number. Yeah. So if we check all the divisors from, let's say, from 0 to, from 1 to, no, not from now, from 2 to n minus 1. We can use Fermat-Little theorem if we work in, if n is prime. We will do it in a second. Now, if n is if n is prime, how can you check the number is prime? Yeah, you can check all the possible divisors up to square root of n. So in times square root of n is pretty simple. Yeah? So we can check all the possible divisors up to square root of n. If none of them divides n, then n is prime. Why so? Because if n is not prime, then n is product of some p and q, and at least one of them must be less than square root of n. Yeah? So any non-prime number, is there a term for non-prime in English? I don't know. So any non-prime numbers have a divisor which is not less or equal than square root of n. So you can just do it like this. Yes, you can use sieve or transference. Yes, that's also possible. I will not talk about sieve because it's not that interesting. No, we can talk about sieve. Okay, we can do it later. Yes, the sieve is used when you need to find small numbers. It's pretty hard to use it when you want to find like 1000 bits prime number. Now, so composite. Oh, so yeah, composite number. Yeah. So if n is composite number, then it has a divisor which is less or equal than square root of n. Cool. Yeah. Now, so this algorithm is not polynomial. Like we discussed in the beginning, the polynomial algorithm means it should be polynomial of the size of the integer. Yeah. So size of the number is log n. So this is not polynomial of log n. So it is slow algorithm. You cannot use it to find really big prime numbers. How to find really big prime numbers? It's a good question. There are several good tests which checks if the given number is prime or not. We'll discuss one of them. We'll discuss Miller-Rabin test. Let's start from the simple theorem. Let's start from the Fermat-Little theorem. Fermat-Little theorem tells you that if number n is prime, okay, let's make an extended version. Let's do the following. Let's see the Euler function. So, what is Euler function of number n? It is the number of integers co-prime with n. Number of, let's say, a co-prime with n, a from 0 to n minus 1. So phi of n is basically the number of integers co-prime with n. Now, if n is prime, then phi of n is actually equals to, so if n is prime, then phi of n equals to n minus 1. Now, really simple theorem. If you take any number, a, co-prime with n, and put it to the power phi of n, you will get 1. Very simple theorem. Let's prove it actually. Let's prove it. We have time. Yes, we have time. So let's prove this theorem. It's easy. So I will not prove any hard theorems, but this theorem is really simple. How can we prove it? No, let's take all possible coprime numbers. So let's take numbers x1, x2, and so on, x, n. So this is set of all numbers coprime with n. So all xi coprime with n. So let's take all numbers coprime with n. And let's multiply them all by this number a. So let's see y1, y2, and so on, y phi of n. Each yi is just xi multiplied by number a. Now, what can we say about here? So now all numbers y are coprime with n. So first observation is yi is always coprime with n. No, why is it true? Because we multiply two numbers, both of them are coprime with n. So if you multiply two numbers coprime with n, you will get some number that is also coprime with n. You don't have any common divisors here, you don't have any common divisors here. If you multiply them, you will not have any common divisors. Now, second observation is that all these numbers y are different. Why is it true? Because we can get from number y to number x just by dividing by this number a. So number a is coprime with n, so we can divide by this number a. So we can calculate this number x from number y just by dividing by this number a. Yeah? So this number x is number y multiplied by a power minus 1. And since the number of these integers is the same, so for each number here we have a pair here, for each number here we have a pair here. So this both sets are actually the same sets. Yeah? So here we have a set of all possible coprime numbers with n. Again, what does it mean? It means that x and y actually contain the same set of integers. Now, since we have the same set of integers, let's calculate the product of these integers. So the product of all integers in set x will be equal to product of all integers in set y. Just because we have the same set of integers here. Yeah? And now this set is just product of everything in x multiplied by y in power of p of n. So, and now in this equation we can just divide both sides of this equation by this product. Since this product is product of numbers coprime with n, so this product is also coprime with n. So we can divide by this product and see that 1 equals to a power of n. Is that some generators? We'll talk about generators in we'll do it in just a few minutes. What is it? Before x. Where? This is phi. This is phi. Which one? Okay. This is the product. So I want to calculate the product for this. So I will want to multiply all numbers in set x. It's just the sum, but product here. So big P. Yes. Yes, capital P is used for product of set of integers. Yeah. Now to the test. So how to test if the number is prime? What you can do? So if you want to check if your number is prime, what you can do? You can take some random number a, coprime with the number. Check if it is coprime. So let's do it like that. Pick some random number. From 0, not 0. I don't want zeros. From 1 to n minus 1. Then check if it is coprime with n. If it is not coprime, then n is not prime. So if GCD of a and n is not 1, then true false. That's called is prime. Prime. N. So take some random number. If it is not coprime, then n is definitely not prime. If it is coprime, let's put it in power n minus 1. So if a in power n minus 1 is not 1, then n is definitely not prime. Because if n is prime, then phi of n must equal to n minus 1. Then we put any number in power n minus 1, we should get 1. If it is not 1, it's not prime. If not, let's say it's true. It's called Fermat test. Very simple test. So again, what we do, we pick some random number and check these basic properties. If they're satisfied, we say, well, okay, it may be prime. Now, if this function returns false, it guarantees that the number is composite. Yeah. So if I return false here or here, I guarantee that number is composite. If I return true, it may be a mistake actually. So this is a randomized algorithm. So sometimes it returns true even if the number is composite. For example, if you pick a equals to 1 here, then it is definitely coprime, and this power is actually definitely equals to 1. Yeah. So if you pick 1 here, then here both these properties will be satisfied. Yeah. So no, you can pick number from 2 to n minus 1 actually, just to avoid this situation. But it's not that important. There will be some coprime numbers which will give 1 when you put them in the power n minus 1. So it may happen. Sometimes you get wrong result from this algorithm. And that's very common in this number theory actually. Many algorithms in number theory do something like that. They pick some random numbers, do some random things, and then hope that everything will go right. What's bad about this algorithm? It's called Fermat test. What's bad about it? For some numbers, the probability of success is very small. So there are some bad composite numbers. They call Carmichael numbers. Doesn't matter. So for these numbers, if you pick any coprime number with n and put it in power n minus 1, you still have 1. But the number n is not prime. So there are some composite numbers which fails this Fermat test. No, it actually happens like because phi of n is actually divisible, is a divisor of n minus 1. So if phi of n is divisor of n minus 1, then if you put it in power n minus 1, it will always be equal to 1. So it happens. Sometimes it happens. What you can do about it? No, let's see. So now there are different types of primality test. I'll tell you how the Miller-Rabin test works. I will not prove it has good probability, but I'll just tell you what's going on in Miller-Rabin test. There's some magic happens actually. So how Miller-Rabin test works? Let's do all the same steps, but make one more check. Let's do the following check. So here I want to calculate a in power n minus 1. Let's split this power n minus 1. Let's put n minus 1 in some power of 2 multiplied by some y. And y is 1. So let's just grab all power, maximal possible power of 2 from this number n minus 1. And now let's calculate the following sequence. Let's calculate, so n power n minus 1 is just n power y, and then power this. Yeah. So yeah. N power n minus 1 is a in power y, then power 2 in power x. Yeah. And now we can split it into steps. So it's power 2, and power 2, and so on. Here x times. So let's calculate n power n minus 1 like this. Calculate n power y, and then calculate square each time. So we have like sequence of this, like a power y, a power 2y, a power 4y, and so on, a power 2x. So let's calculate this sequence. Now, in this sequence, this number should equal to 1. Definitely. Right? Now, let's go back here until we find any number which is not 1. So this number is 1, this number is 1, this number is 1, this is not 1. Let's look at this number. So let's find the first number which is not 1. Here. Well, let's say we have some number. Which letter we don't have? I have too many letters here. I need one more letter. Let's number k. So let's have integer k. Yeah. So again, we calculate this sequence of powers of a, and now go back from here and find the first integer which is not 1. Now, if this k is not equal to 1 and not equal to -1, then n is not prime. So if k is not equal to plus or -1, then n is composite. Why is it true? Let's see. So if k, so here, what do we have here? We have k and then 1. So this next number is k squared. So we have k squared equals to 1 modulo n. Let's put it to the left. So we have k. No. Okay, let's do it in 2 steps. We have k squared minus 1 equals to 0. Now, k squared minus 1 is k minus 1 multiplied by k plus 1. Now, if k is not equal to plus or minus 1, then this part is not 0, and this part is not 0. So we have product of two non-zeros equal to 0 modulo n. It can't happen if n is prime. Yeah, so if n is prime, then if you take product of two numbers with none of them is divisible by n, then the product is also not divisible by n. So again, okay, so this is not 0, and this is not 0. If you have product of two numbers not zeros equal to 0, then n is not prime. Ta-da. Actually, you can calculate the divisor of n. You can take GCD of this and calculate the divisor of n. That's all. That's all modification to this primality check. So we'll do all these checks and also take this check. And the magic part is that if you do it like this, then probability of failure will be something like 1/4. So like 75% times will be accurate. So it's hard to prove. We need to go deep in this number theory. We will not do it today, but the idea is if you take the set of all possible bad numbers, they call liars in this. So there are witnesses and liars. So if number n is composite and you pick some random number here and you have all these checks passed, it's called the number A is a liar. Yeah, so it gives you the wrong result for this test. And the major result of the Miller and Rabin test is that the number of possible liars is no more than n over 4. So at most 25% of all integers in this set are liars. So the probability that you pick one of them is like 25%. Yeah, so basically what you can do, you can run the same test like 20 times. And if you do it 20 times, probability will be 2 in power of 40. Yeah, it's usually good enough. So again, here you can modulate it. So you can like there's a good probability. There's some probability. Yeah. So if you want to increase the probability of success, you just run the same algorithm over and over again, and just the more you run the algorithm, the probability of failure will be decreasing in exponentially. So you can run it hundred of times and be totally sure that your number is prime. Nice. Oh, okay. What's next? Let's talk about factorization. factorization is all different. So factorization is a problem. You give a number n, and you want to split it into some product of some primes. So again, that's the main theorem of arithmetics, is that any integer number can be decomposed into some product of primes. So it's like p1 power a1 multiplied by p2 power a2, and so on. So any integer number can be decomposed into some product of some primes. And the problem of factorization is, so you give a number n, and you want to find the set of these prime numbers. But actually, even if you find at least, if you can find at least one divisor of n, it still be good enough, because if you manage to find at least one, if you're given some composite number and you manage to find at least one of its common divisors, you can then repeat the same process. So if you give a number n and you have algorithm which gives you any divisor of number n, then you can take these divisors divided by this divisor and then repeat the same process. So the problem will be you give a number n and you want to find any divisor of this number n if it is not prime. What's interesting about factorization problem is that we don't know any polynomial time solution for this problem, and we actually hope very much that there is no polynomial time solution for this problem, because if there is polynomial solution, then we will have very big problems in modern cryptography, and we'll discuss it next week. So we don't know any polynomial solution for the factorization problem. There is an algorithm for quantum computer. There's quantum algorithms which claims to factorize numbers in polynomial time, but there is no, quantum computers are not ready yet. We really hope. Maybe in some secret laboratories there are big quantum computers which able to factorize big numbers, but there is no evidence of this right now. If it will be a big problem. Okay. So, again, how to factorize number if non-polynomial solution? Well, again, you can do it in. You can do it like we did with primality. You can check all the divisors up to square root of n. So in time, square root of n is quite simple. Yeah. So you can iterate all possible divisors up to square root of n. And again, if it is not prime, you will find some divisor. You then divide by this number and so on. Can you do it faster? There are fast algorithms. So there are pretty fast algorithms to factorize numbers. Not polynomial, but pretty fast. They still can factorize these 1000-bit numbers. But we hope they will not. But they are pretty fast, actually. Should we discuss polar factorization or not? I'm not sure we have time enough for this, but okay, we may discuss some polar algorithm or not. I'm not sure. Do we have enough time to discuss polar? I actually want to discuss generators more. Okay, let's talk about generators first. Sorry. So this is not polynomial algorithm. Again, like we discussed in the beginning of the lecture, the polynomial algorithm must be polynomial of logarithm of n. So the size of the problem is the length of the number. Now, let's talk about generators. Let's take prime number. So let's take some prime number. Let's take some prime number. What is a generator? Generator is a very simple thing. Generator is a number such that if we... Let's look at all possible powers of this number. So this is the power 0, z power 1, z power 2, and so on, z power p minus 1. So this number is definitely 1, this number is definitely 1. So if you continue this sequence, you will have the same period, right? So g power p will be the same as g power 1. Yeah. So if you look at the infinite sequence of these powers of g, you will have some periodic sequence with period equal to p minus 1. So here you have some period. What is generator? Generator is a number such that in this period all numbers are different. So I want all numbers from g0 to gp minus 2 different. And g is generator. It's called generator or primal root, it depends on what. Let's say it's called generator. So the generator is a number such that if we look at all powers of this number from 0 to p minus 2, we'll have all possible numbers from 1 to p minus 1. Well, for example, let's take prime number. Which one? Let's take 11. Now let's take any number and check if the number is generator. For example, let's take number 2. Is 2 a generator modulo 11? Let's check. So let's calculate all powers of this number 2. We'll have power 0 is 1, g power 1 is 2, and so on. So we have 1, 2, 4, 8. Then we have 16 modulo 11 is 5. Then multiply by 2 we have 10. Multiply 10 by 2 is 20. Modulo 11 is 9. 18 modulo 11 is 7. 7 with 14 modulo is 3. 6. And 1. So g power 1 and so on. This is g power 10. So we can see that here we have all possible numbers from 1 to p minus 1. If you have a situation like this, then G is a generator modulo p. How to find a good generator? Good news and bad news. Good news is there are many generators for each prime modular. So for any prime number, there is a big number of good generators. The bad thing, we don't know how to find them efficiently. So we will just pick random number and check if this number is a generator. So very simple algorithm. We know there are many generators. So we'll pick random number from 1 to p minus 1 and check if this number is a generator. And since the number of generators is pretty large, then we will find a good generator with good probability. This simple algorithm. Now, how to check if the number is generator? Why isn't every number a generator? No, because sometimes it's not. Let's find some number which is not a generator. Let me see. Okay, for example, for p equal to 7, let's we take g equal to 2, yeah. And what we'll have? We have g power 0 is 1, g power 2 is 2, g power 3 is 1. 2 is 4, g power 3 is 1. That's all. Again, let's put all of them. G is 6. So 2, 4, 1. Yeah. So the length of this period is less than 6. So I want this period to be of length 6, but here I have period of length 3. So it happens. For some numbers, the length of this period will be not 6, not p minus 1, but smaller. Okay, so not every number is a generator, but there are many generators. So if you just pick random number, with good probability you will pick a good generator. The only thing we need to do is to check if the given number g is a generator. How to check if g is a generator? Well, what you can do? If you have some number p, you have some number g. How can you check if g is a good generator? What you can do? Well, first of all, you can check all possible powers of g, right? And just check that all of them are different. But it's too slow. Yeah. If you just check all possible powers, there are p minus 1 powers. P is big number, so it's just too slow. The idea is that it is enough to check not all powers of g, but just some important powers of g. What do I mean? Let's see. Oh, here is actually clearly so. So let's take let's look at all these numbers. Yeah. So that we know that for any number g, even if it's not a generator, g in power p minus 1 will be equal to 1. So we know that p minus 1 is actually a period of p minus 2. P minus 2. Minus 1. Minus 1. P minus 1 is actually the period of this sequence. Yeah. So if I pick any number g, not only generator, but any number g, p minus 1 will be a period of this sequence. What's problem here? Problem here, again, like here, 6 is also a period of this sequence. The problem here is that I have a smaller period. So I have period 6, but I also have period 3. Yeah. So if I have a period which is shorter than p minus 1, then it is not a generator. So what I need to do? I need to check if my sequence, this sequence, has a period less than p minus 1. Yeah. What can be the length of the period? What do you think? If the length of the period is not p minus 1, then what can be the length of this period? What do you think? Here is actually quite clear, yeah? Yeah, it should be some factor of p minus 1. So I can check not all possible, not all powers of g, but only check the powers which are divisors of p minus 1. So if I have p minus 1 equal to, no, here, if I have p minus 1 equal to 10, then the possible periods will be 2 or 5. Yeah? So if period is not 10, it must be 1, 2, or 5. So how to check if the period is, how to check if period is 1? So if period is 1, then I need to check this position. I need to check this position and check if it is not 0, not 1. If period is 1, then g power 1 must be 1. I check this power, check it is not 1. Now, if period is 2, then g power 2 must be 1. Yeah? So I check this position. If period is 5, then g power 5, then 1, 2, 3, 4, 5. This power. So, to check if number g is a generator, I only need to check these 3 positions. Yeah. The problem is that the number of divisors is still very large. So for number p minus 1, there may be a big number of possible divisors. So that's not all. It is sufficient not to check not all the divisors, but only some divisors. Let's look here. Let's say, for example, p equals to 61. Yeah? So I have p minus 1 equal to 60. I have my period. I have my period of 60. So I have this g power 0, g power 60. I claim there is a small number of divisors I need to check, and it will guarantee that there is no period of length less than 60. What do you think? Which periods are actually important to check? Okay, let's start from here. So what I want to do, I want to check all possible divisors. If I have divisors 2 and 3, not exactly. It's close, but from opposite side. Yeah. So for example, I check that there is no period 2 and there is no period 4. Okay. If my sequence is periodic with period equal to 2, then it is also periodic with period equal to 4. Yeah? So if I have period 2, then I will also have a period 4. Right? Again, if I have something like this, or if I have 1 and here I have 1, then in position 4 I also will have 1 because I have period equal to 2. So if I have period 2, I will also have period 4. So I don't need to check period 2. I can check only period 4. And if there is no period of length 4, then there is no period of length 2. Right? So if I need to check periods 2 and 4, I actually need only check period 4. If there is no period of length 4, then there is no period of length 2. But then, if I have period of length 4, then I must have period of length, let's say, 12. Right? Now again, if I have period of length 12, then I have period of length 4, then I have period of length 2. So it's enough to check period of length 12. Yes, what you need to do is to check periods which are a fraction of, so you only need to check periods like x, which is p minus 1 divided by some prime. By some d, because d is a prime factor of p minus 1. For example, for 60, so what is 60? 60 is some power of 2 multiplied by power of 3 multiplied by power of 5. So there are 3 prime divisors of 60, 2, 3, and 5. So it's enough to check only periods of length 20 or 30, yeah, divided by 2, 20 and 12. So we only need to check these 3 lengths. If we don't have period of length 30, we don't have period of length 20, we don't have period of length 12, then there is no period of length less than 60. Because any other length of the period will be part of these periods. Yeah? If you have period of length 6, for example, yeah, then you will have period of length 12, and you have period of length 30. If you have period of length 4, then you have period of length 12, and so on. So for each smaller period, if you have this small period, then you have this period as well. So you only need to check these 3 values. And now, since the number of prime factors is no more than log n, you may not have more than logarithm of divisors, of prime divisors. Yeah. So you only need to check up to log n places in this sequence. And if there is no period in this, if these powers are not ones, then you have period only of length p minus 1. Then it is a good generator. The only problem here is that to find these prime factors of p minus 1, you need to factorize number p minus 1. And as we discussed before, there is no good way to factorize numbers. So in order to find the good generator and just do it like this, you kind of need a good prime number. You need prime number p such that p minus 1 have some good factorization. Sometimes you like it, sometimes you not. It depends. So sometimes it just happens that p minus 1 have a good factorization, so you can find it fast. If not, then it's bad prime number. You cannot find good generator. Okay. Is it enough for today? Yeah, I think it's enough for today. I want to discuss polar factorization. Let's discuss polar algorithm. Okay, let's do it. Yeah. Okay, let's discuss factorization algorithm, which works in time this. So I want to root of 4th degree. So it's faster than just iterate all divisors up to square root of n. So I want to factorize number n in this time complexity. Very cool algorithm. So what I will do? Let's do it like this. So, first idea. If n is composite, then n is product of some p and q. And one of them is less than square root of n. Now, let's do some magic stuff. Let's take some function. F of x. Let's say, for example, I don't remember, x plus 1. Something like that. Let me check quickly. Plus 1 or minus 1? It's magic, so sometimes you need to check if your magic is right. Minus 1, okay. Minus 1. Maybe plus 1 also works. Yeah, they say plus 1 also works. Okay, now let's put it back. Now, there is some function. This function is pretty much random. So, like the behavior of this square function modulo n is everything happens modulo n. Yeah. The behavior of square function modulo n is pretty much chaotic. So it will give you something very much random result for different numbers, and we will use it. Now, let's calculate the sequence. So we start from some number x0, and then calculate x number x1, and so on. Each next number will be just f of xi minus 1. So let's calculate the sequence of numbers, like infinite sequence, and so on, and so on, and so on, and so on. And let's calculate the sequence until we find some loop. So at some point we will find the cycle like this. So we'll have the numbers we already have before. Now, the interesting observation. What will be the length of this cycle? What do you think? if you have some random function, let's believe that this function is pretty random. Right? Then you iterate over some numbers modulo n. So there are n possible numbers. And you just jump between these numbers using some random function. How many jumps will you make until you will find the number you already seen before? Again, basically what happens? You jump into some random points from 1 to n. Yeah? From 1 to n minus 1. From 0 to n minus 1. Yeah? So you jump into some random points from 0 to n minus 1. And you stop when you jump into some number which is already seen before. So how many random jumps can you make until you visit the same point twice? Have any intuition? I believe we discussed it when we talked about hash tables, like that. Yes, maximum is n, but what is the average size? So if function is really random, so what is the expected number of jumps? Yes, it was a long time ago. It was at the end of the first semester when we discussed the hash tables. The interesting thing that the number of jumps will be about square root of n. So the length of this loop will be about square root of n. Why is it true? Because of the what's called birthday products. Yeah. So if you just pick random values, if you pick some square root of n random values from 1 to n, then with good probability you will pick the same number twice. No, that's actually because if you have square root of n numbers, then you have n pairs. Yeah. So the number of pairs in your group is square of the size of the group. So if you have square root of n numbers, then you have n pairs. So each pair may have a collision. So if you have square root of n numbers, there is a good probability of collision in your set. Yeah? And that's exactly what happened here. So we just pick random numbers until we find some collision. And we will find the collision after about square root of n steps. That's not all. So how will it help us to factorize number? Well, first of all, we will find a cycle in square root of n. And I promised you this time complexity. So it's not enough. Yeah? Secondary, how actually this cycle will help us to factorize number, but it will help. Let's look at the following values. Look at the values y equals to xi modulo p. So we have some divisor of n. Yeah. So we know that we have some divisor which is less or equal than square root of n. Let's look at the numbers xy modulo this divisor of n. We don't know value of p. But let's just imagine we know the value of p. What will happen if we look at the same situation for numbers y? So we have number y0, y1, y2, and so on. What will be the length of this period? The length of this period, since we take all the numbers modulo p, the length of this period will be square root of p. Again, we have p possible values for the number y. So after these many steps, we will have some collision. And square root of p is about square root of 4n. So since p is less than square root of n. Now it's interesting. So if we look at this, if you look at this sequence modulo p, then we will have loop after root of 4th degree of n. Now the tricky part. Tricky part is we don't know p. If we know p, it's quite obvious how to factorize, right? So we don't know number p. But we know that there is number p. And after these many steps, we will find the loop modulo p. So how to find this loop? There are many ways to do it, actually. No, one of the ways to do it is the following. Let's make 2 pointers. Again, what happens? What happens if I have a period? If I have a period modulo p, it means that I have some xi equals to some xj modulo p. I don't know modulo p, don't know. But what I can do, I can make take difference of these numbers, xy minus xj, 0 modulo p. And now I have some difference, which is divisible by this p. Yeah? So how to find p? I can calculate greatest common divisor of xi minus xj and n. And it will give me some divisor of n. No, it's also a case that I have period modulo n. That's a bad case. Sometimes you have a period modulo n. Then you just pick another random number and start process all over again. Yeah. But if you have period modulo p, but not period modulo n, then you have two different numbers, and they're divisible by this p. So you take difference of the numbers. This number is not 0. So if this difference is 0, then you failed. You just start all over again. If the difference is not 0 and is divisible by this p, then you can calculate GCD of this number and n. It will give you some divisor of n. Not p maybe, but some divisor of n. It will be something kn, kp. So it will some divisor of n. Now, how to find out that we actually have a period modulo p? We can't. But we can look for the period using the following algorithm. Very simple algorithm. There. Let's take 2 pointers. x1, x1, x2, and so on. Oh, that's circles. Let's take 2 pointers and put them here. So first pointer is here, second pointer is here. Now, each time we make one step. First pointer we move 1 step forward, and second pointer we put 2 steps forward. So we move this pointer here, and this pointer here. Then again we move this pointer here, and this pointer here. So basically, we consider only pairs xi and x2i. Let's consider only pairs like this. What will happen? At some point, there is a period. Yeah? So there is a period of some size. At some point, I will be somewhere here and 2i somewhere here. Now, the difference between 2i and I is I. So it is difference between these two indices is increasing. So at some point, this difference will be divisible by the length of this period. Again, we don't know the length of this period. So we just increase this difference until it will be divisible by the length of this period. At some point it will be. So when this length is divisible by the length of the period, we will have 2 numbers with difference 0 modulo p. Again, we don't know modulo p. We don't know the length of this period. But if we just check these pairs, then at some point we will find 2 elements in the same position in this period. So we'll have 2 numbers with the same remainder modulo p. Yeah? Despite the fact that we don't know modulo p and we don't know the length of the period. And since the length of this period is about root of the 4th degree of n, the total time complexity will be the same. Yeah? That's all. So okay, this is one of the easiest algorithms to factorize number faster than just iteration over all square root of n divisors of n. Okay, that's definitely enough for today. Okay, see you next week.